Hi guys, today I'm gonna talk about one of the most famous protocols in embedded software development. It's called I2C or I2C. It stands for Integrated Circuit, and this protocol allows multi-point-to-point communication between different elements or devices on the embedded solution. And it is a master and slave configuration, and it will allow distances of communication be up to several meters and around 1008 slaves. So what I'm talking about is a bit historical here. Of course, the modern versions of I2C is more robust, allows more devices, more distances, and so on. This is one of the basic examples, like school examples, how to use I2C. So I2C is using two-wire interface, SDA and SCL. SDA stands for serial data and SCL stands for serial clock. And the question here is, why is clock necessary? Well, for example, if you have two devices, device 1 and 2, and you have a video explaining serial communication between PC and the board, where PC is device 1 and the board is device 2, and they are also using serial communication in this case. To simplify things, you have a pin, which is a digital pin, TX and RX, and on the other side you also have a TX and RX. So when device 1 wants to send a 1 bit or beginning of data, it will use digital write here, high, and then low once it's finished. And the signal this one, will propagate through the wire to the other device. And other device will call digital read on RX pin. So I don't know if you can see the problem here. I'm sending the data travels. This traveling distance also takes time. And once it reaches the other device, I need to initiate reading. And the problem is, I don't know when the device is sending the data. So that's why I need a rhythm saying when to read and when to write. So once all devices can hear the rhythm, they can synchronize their writings and readings, so the communication would be possible. So the worst case scenario would be that I send the data and the device 2 miss this data by not reading at exact time. That's why we need a clock telling devices when to read and when to write, so they can speak to each other. Of course, this works on the other line as well. So this is a simplified version of I2C protocol, and I will not cover all of these, just basics. And as I mentioned before, the modern version is way complex than this one. In essence, the I2C protocol has two parts. The first one is address part, and the second part is data. And in address part, you can see that you have 7 address bits that you can use to address each slave in configuration. And this address should be unique for every device, because it's only 7 bits and it's obviously very limited address space. Manufacturers usually allow change of the address, whether by physically connecting two pads or jumpers, or on a software level you can also change the address. Nevertheless, what's important here is that you have two wires. The first wire is serial data, that is actually sending the data, and the serial clock is actually the clock dictating the rhythm for all the slaves and master in configuration. So the master device is sending the clock, and the master is also initiating this first part of SDA. In the beginning, so the master is sending the address, and all of the nodes in the network, kind of a network, are connected to those two wires, and all of the nodes are listening to address. If I'm the node with the address being broadcasted like this, then only I will respond as a device, as a slave. And the next bit after the address is read or write bit. If it's 1, the master is requesting the data. If it's 0, the master is sending the data. It actually defines who will speak in next part of the communication. And this is some acknowledge bits and so on. Let's ignore this for now. And after that you have some period of delay. During this time, device could gather data or whatever is necessary. But if I'm sending 0 here, it means that the master is going to send the data, and all of the slaves should listen, especially the slave that's being addressed. So if I want to send the data to a specific device, I will set its address here at the beginning, and then I will send the data, and the data is just 8 bits, 1 byte. And after that also you have acknowledgement and so on. I will ignore this part as for now. And that's it. If you want to send a 1 byte to a device, you need to send its address and send highs and lows, zeros and ones of a byte. So for each byte you send the address as well. That is very, very inefficient. However, it's very practical, and it's widely used in embedded software development, because I think it was introduced by Philips for their TVs, because they have lots of they obviously recognized the issue of multiple devices communicating using the same channel, the same bus, same 2 wires. So they introduced I2C protocol for their TVs, and now it's being very, very used in hobbyists, and of course even in commercial products as well, especially in the commercial products, because these are very short distances and the timings are very precise. The latency is here not important at all. The throughput is also not important, and but for our case it's going to be perfectly fine. On the other hand side, you have the clock dictating the rhythm, which also dictates the rhythm of readings and writings. And one other scenario is where here we have a number 1 being sent. It means that the addressed slave needs to write on a wire, and while the slave is writing on the wire, the master is listening for the data on a serial data line. And this is it. This is how I2C works. It says it's all buttons and LEDs on a micro level. Well, if you remember this, we had a video of interrupts. We attached a single wire to interrupt, which is here the case. If you attach, and this is obviously implemented like this sometimes, if you attach interrupt on the SCL, you will get interrupt each time the clock rises, and then you will do the reading and writing and so on. You can actually write your own implementation of I2C protocol using just interrupts, as mentioned before. And one of the devices here that are using I2C is accelerometer. It's I2C based, it's a triple axis accelerometer, and it allows 2, 4 and 6 Gs, and we will just connect the accelerometer and read accelerometer data. The accelerometer here is this device. It has the pins marked 3.3 SDA, SCL, I2, I1 and ground. We will ignore I2 and I1, just connect those for I2C. And let's start a new project. I will create a project called, not here, called ACC, like for accelerometer. Okay, and just a second. HD, IOT, choose ACC, the name of the project, it will be created. And what we can do now is install the library for this and go to find libraries. Which library, and now we need to write the name of the board. If you take a look on the chip of the breakout, you can actually see the name. It says MMA8452. Just write that here, MMA8452, and it should be found in the library. Sorry, I have MMA. I'm just gonna search for MMA. So it's MMA Spark Fun MMA8452Q. You can actually search for this because it says it's a particle library for Spark Fun. Copy this and install library. Which library? The one that you have just copied. And it's already installed. And if you take a look in the lib folder, you have the examples of this library, how it's used. I will just copy everything and paste, and we will analyze how it works. I will paste over my code, empty code. Just zoom in a bit. Okay. And yeah, it's all, the library is here, and we can actually flash the code, cloud flash, device name, the one I have here. And if everything is fine, but I forgot to connect the chip on the board. So sorry about that. Let's disconnect the board before working with anything. There, it's disconnected. The connection is very simple. You just follow the instructions on the board. So I'll just move the breakout here, the sensor here, connect the bottom one to the ground because it says G and D, and the voltage one is 3.3. Also be careful not to put it in VUSB because that's going to be too much, because VUSB is 5. And SDA goes to SDA, and you have SDA here on top. It says D0 for SDA, and clock, the white one is going to be a clock, is next to it, and that's it. This is how you connect the board. And now you can cloud flash because I already flashed. You can do it again. It has the code. And you can open the serial monitor. You can use a PuTTY or use the one on in Visual Studio Code. Let me just hit reset to see if the data is being sent. Maybe I need to flash. Wait for it. Cloud flash, but I did. It should print the data. Now it's being flashed again. Maybe the first time it didn't succeed. Unfortunately, yeah, something is wrong. Maybe I made the wrong connection. See, this is SCL SDA 3.3, and this is ground. I hit reset, And another issue that might be is that my accelerometer is a bit broken. A moment please while I search a new one. Just gonna change it. Oh yeah, I know what was the problem. Ah, silly me. Check this out. So I had this one, it didn't work because you have here SA0, it's another address, it's not a default one. Because I put the bit of LED here, thin LED, and now I have connected those two pads to select a different address, so it was using another address. That's why it didn't work. I could use, I could change the address in the code, but I just swapped with the different kind. And now if I connect the board, check the serial monitor, you will see the data being sent here in the terminal. Okay, and monitor, this is very important, let me just emphasize this. While testing the board, it is very important to hold the wire when you're gonna swatting around with the board itself. So you can actually break this USB connector here if you do not hold the wire firmly so it doesn't shake a lot. And please do not shake the board because it's enough to turn it down and you can actually see the changes in the graph. And this sensor is very, very sensitive to the changes in orientations and accelerations, and it is very precise. It is that precise that it can recognize the knocking on the table as a vibrations, and there is and the manufacturers are aware of this, and they actually put this tap recognition into the library, which you can use in your project's ideas. So you can actually have a knocking detector and to do something like extra notification if someone is knocking on your door. Okay, you can we can unplug this part, and that's it. We are done with the introduction to accelerometer. I hope you had fun and that you can make something great out of it. See you next video.